November 29, 1944. Central Aerodynamics and Hydrodynamics Institute, outside Moscow. Chief Engineer Andrei Tupolev stood before the most sophisticated aircraft that had ever landed on Soviet soil, his engineering team assembled in the freezing hangar with notebooks already open. The Boeing B-29 Superfortress stretched before them, its polished aluminum skin reflecting the dim overhead lights, serial number 42-63565 stenciled on the tail. This single American bomber, forced down during an emergency landing at Vladivostok after a raid on Manchuria, would trigger the most ambitious reverse engineering project in Soviet aviation history and reveal truths about American industrial capability that would fundamentally alter Stalin's understanding of the technological gap between East and West. The aircraft bore the name Ramp Tramp painted on its nose, belonging to the 771st Bombardment Squadron of the 462nd Bombardment Group, operating from bases in China against Japanese targets. Captain Howard Jarrell had brought the crippled bomber down at Central Airport in Vladivostok on July 29, 1944, after battle damage and fuel exhaustion made reaching American bases in China impossible. Soviet authorities, technically neutral in the Pacific War despite their alliance with America against Germany, interned the crew according to international law while secretly beginning the most comprehensive technical intelligence operation in Soviet military history. The bomber represented technology that Soviet industry had never produced, incorporating innovations that Soviet engineers had theorized about but never successfully implemented at scale. 2 more B-29s would follow in the months ahead. On November 11, 1944, Captain Weston Price landed his damaged Superfortress at the same Vladivostok airfield, bringing the total to 2 intact American heavy bombers in Soviet hands. Then on November 21, 1944, less than 2 weeks later, a third B-29 arrived under similar circumstances, completing what Soviet intelligence considered an unprecedented windfall of American military technology. 3 identical aircraft, all operational despite battle damage, all built to the same specifications by American factories, all containing the same revolutionary systems that Soviet aviation had struggled for years to develop independently. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Stalin himself had ordered the systematic exploitation of these captured aircraft with explicit instructions that reflected his understanding of their strategic importance. Copy everything. Reverse engineer every component. Reproduce the bomber exactly as the Americans built it, regardless of the cost or effort required. The directive came directly from the Supreme Leader, bypassing normal procurement channels and military aviation development programs. Soviet industry would build an exact duplicate of the B-29, creating a Soviet heavy bomber capability years ahead of anything Soviet designers could develop independently through conventional research and development. The Central Aerodynamics and Hydrodynamics Institute, known by its Russian acronym TSAGI, served as the Soviet Union's premier aviation research facility, roughly equivalent to America's National Advisory Committee for Aeronautics. Here, the nation's best aeronautical engineers conducted wind tunnel testing, structural analysis, and flight dynamics research that informed Soviet aircraft development across all categories. The facility employed thousands of engineers, technicians, and support personnel, many of them veterans of pre-war Soviet aviation projects that had established the USSR as a significant player in aviation technology during the 1930s. But nothing in their experience had prepared them for the complexity they encountered when they began dismantling the first B-29. The initial inspection conducted in late November 1944 revealed aircraft systems that seemed impossibly sophisticated compared to anything Soviet factories produced. The pressurized cabin, maintaining sea-level atmospheric pressure at altitudes above 30,000 feet, used technology Soviet designers understood theoretically but had never successfully implemented in production aircraft. The remote-controlled gun turrets, operated by gunners using computing gun sights that automatically calculated lead angles and deflection, represented fire control sophistication that Soviet weapons designers had discussed in technical papers but never built into functioning hardware. The reversible pitch propellers, which could reverse thrust direction to shorten landing distances, incorporated hydraulic control systems more complex than anything Soviet factories manufactured for any purpose. Every system revealed American engineering approaches that differed fundamentally from Soviet practice in ways that went far beyond simple technical specifications. Where Soviet aircraft used welded steel tube fuselage structures covered with fabric or plywood, the B-29 employed stressed aluminum skin construction with integral stiffeners that made the skin itself a load-bearing structural element. Where Soviet bombers relied on manually operated defensive guns with simple iron sights, the B-29 featured remotely controlled turrets with computer-assisted aiming that dramatically improved hit probability. Where Soviet heavy bombers struggled to reach 20,000 feet with useful bomb loads, the B-29 operated routinely above 30,000 feet where Soviet fighters could barely intercept and anti-aircraft artillery became largely ineffective. The global strategic situation in late 1944 made possession of these bombers particularly significant for Soviet military planning. Germany faced inevitable defeat as Soviet forces advanced relentlessly westward, crushing Army Group Center and approaching the German border. Japan, though still fighting across the Pacific and in China, would eventually collapse under American pressure, leaving the Soviet Union as the only potential rival to American global influence in the post-war world. Stalin understood, even as Soviet and American forces fought as allies against the Axis powers, that the wartime partnership would not survive into peacetime. The atomic bomb project, which Stalin knew about through his intelligence networks even though Roosevelt had shared no official information, would give America devastating military superiority unless the Soviets could develop comparable delivery systems and eventually atomic weapons themselves. Soviet heavy bomber development had lagged behind American and British programs throughout the war due to fundamental industrial limitations and strategic priorities that emphasized tactical aviation supporting ground forces. The Petlyakov P-8, the USSR's only four-engine heavy bomber designed to see production, remained largely experimental with fewer than 100 built. The Tupolev TB-3, a corrugated metal giant from the early 1930s, had become obsolete by the war's start but continued flying transport and paratroop missions because nothing better existed in sufficient numbers. Soviet industry produced excellent fighters like the Yakovlev Yak-3 and capable ground attack aircraft like the Ilyushin Illinois II Shturmovik, but strategic bombing capability remained beyond Soviet technological and industrial reach. The Americans, by contrast, had developed strategic bombing into a comprehensive military doctrine backed by enormous industrial capacity. Boeing's Seattle factories, Douglas plants in California, and numerous subcontractors across the United States produced B-29 Superfortresses at rates that seemed impossible to Soviet observers who understood industrial production challenges. Each B-29 contained approximately 55,000 individual parts manufactured by hundreds of suppliers, assembled by thousands of workers, and delivered to combat units at rates exceeding 100 aircraft per month at peak production. The complexity of coordinating such manufacturing networks, maintaining quality control across dispersed suppliers, and achieving the precision tolerances required for pressurization and other advanced systems demonstrated industrial maturity that Soviet planners recognized they fundamentally lacked. Tupolev himself, despite being one of the Soviet Union's most accomplished aircraft designers with numerous successful designs to his credit, approached the B-29 reverse engineering project with considerable trepidation. He had been arrested during Stalin's purges in 1937, spending time in a special prison for technical specialists where he continued designing aircraft under NKVD supervision. Released in 1943 after proving his continued value to the state, Tupolev understood that failure on a project personally ordered by Stalin could result in his permanent disappearance. The stakes went beyond professional reputation or technical achievement. Successful reverse engineering would secure his position and possibly his life. Failure would have consequences he preferred not to contemplate. The pressure from above manifested in weekly meetings where NKVD officials demanded progress reports and explanations for any delays. Tupolev found himself walking a dangerous tightrope between technical honesty about challenges his teams faced and political necessity of demonstrating acceptable progress towards Stalin's impossible deadline. Engineers working under him understood the stakes as well, creating an atmosphere of intense pressure where technical problems became potential political dangers. A component that couldn't be replicated wasn't just an engineering challenge, it was evidence of possible sabotage or insufficient revolutionary enthusiasm that could trigger investigations. The engineering team assembled for the project represented the best talent Soviet aviation could mobilize. Specialists in aerodynamics, structures, power plants, hydraulics, electrical systems, and manufacturing processes received orders to report to TSAGI for a project of highest state priority. Security surrounding the work remained absolute, with NKVD personnel monitoring all activities and restricting information flow even within the project team. Engineers worked in isolated groups, each team focusing on specific aircraft systems without necessarily understanding how their work fit into the larger whole. This compartmentalization, standard practice for sensitive Soviet projects, would create coordination challenges as the reverse engineering effort progressed. The systematic dismantling began in early December 1944 with detailed photography of every component, every system, every structural joint before anything was removed. Soviet photographers documented the B-29 from hundreds of angles, creating visual records that could be referenced throughout the copying process. Measurements followed photography, with engineers using precision instruments to record every dimension, every angle, every radius, and every clearance. The data would fill thousands of pages of technical drawings that Soviet draftsmen would create as they translated American design into formats Soviet factories could use for production. The measurement process itself revealed unexpected challenges that highlighted differences between American and Soviet industrial standards. American engineers had designed the B-29 using inch-based measurements while Soviet industry worked exclusively in metric units. Simply converting dimensions from inches to millimeters introduced rounding errors that, when accumulated across thousands of components, could create assembly problems. Tupolev made the controversial decision to maintain American units throughout the copying process, requiring Soviet factories to retool and Soviet workers to learn a foreign measurement system. The decision proved correct from an engineering standpoint but created enormous practical difficulties in production that would plague the program for years. The pressurization system commanded immediate attention from Soviet engineers who recognized it as the key enabling technology for high-altitude operations. The B-29's pressure cabin, sealed with rubber gaskets and maintained by engine-driven compressors, allowed the crew to operate in shirt-sleeve comfort at altitudes where unpressurized aircraft required heavy electrically heated suits, oxygen masks that made communication difficult, and constant vigilance against frostbite in temperatures that could drop below -60 degrees Fahrenheit. Soviet attempts to develop pressurized aircraft during the late 1930s had founded on manufacturing quality problems that prevented achieving reliable seals, and power plant limitations that made driving compressors while maintaining adequate engine performance impossible with available Soviet engines. Engineers examining the B-29's pressurization system discovered American solutions to problems that had defeated Soviet designers. The cabin pressure differential of 8 pounds per square inch, maintained automatically by regulators that sensed altitude and adjusted compressor output accordingly, required structural strength in the fuselage that Soviet aircraft simply didn't possess. American engineers had designed the entire forward and aft pressurized compartments as cylindrical pressure vessels with reinforced bulkheads at each end, distributing pressure loads through the structure in ways that minimized stress concentrations. The sealed hatches, emergency pressure relief valves, oxygen backup systems for emergency depressurization, and crew communication provisions all demonstrated systematic attention to every aspect of pressurized operations. What impressed Soviet engineers most about the pressurization system was not the theoretical sophistication, which Soviet aeronautical scientists understood perfectly well, but the manufacturing quality required to make theory function reliably in practice. The rubber gaskets sealing hatches and access panels maintained their elasticity and sealing properties across temperature ranges from desert heat to stratospheric cold. Soviet rubber compounds degraded rapidly under such conditions, becoming brittle at low temperatures or losing resilience at high temperatures. American materials science had produced synthetic rubbers with properties Soviet chemistry couldn't match, requiring Soviet engineers to either develop equivalent materials or accept that their copies would leak more than American originals. The gun turret system represented another quantum leap beyond Soviet defensive armament technology. The B-29 carried 12 Browning M250 caliber machine guns in 5 turrets, 4 of them remotely operated from sighting stations inside the pressurized cabin. This arrangement allowed gunners to aim and fire defensive weapons without exposure to the hostile environment outside, maintaining full combat effectiveness at altitudes where traditional open gun positions would be impossible to operate. The computing gun sight, developed by General Electric specifically for the B-29, automatically calculated the lead angle required to hit maneuvering targets by solving the fire control problem mathematically based on inputs from the gunner tracking the target. Soviet weapons engineers dismantling the fire control system found complexity that exceeded anything they had encountered in Soviet or captured German equipment. The system used analog computers, mechanical devices using gears, cams, and linkages to perform mathematical calculations continuously as combat situations changed. Range estimation, target angular velocity, projectile ballistics, aircraft motion, and wind drift all factored into the continuously updated firing solution that positioned the guns for maximum hit probability. German fighters attacking B-29s in the final months of the Pacific War would discover, just as Luftwaffe pilots had learned against B-17s over Europe, that American defensive firepower backed by sophisticated fire control proved devastatingly effective against conventional fighter attacks. The precision required in the fire control computer's mechanical components challenged Soviet manufacturing capabilities in fundamental ways. Gears needed to mesh with minimal backlash to prevent errors in the computational output. Bearings had to rotate smoothly without binding or excessive friction that would introduce errors. Cam profiles required precise machining to generate the correct mathematical functions. Soviet machine tools, adequate for most military production, lacked the precision needed to manufacture these components to American specifications. Soviet factories would need new equipment, new training programs for machinists, and new quality control procedures before they could produce fire control computers matching American performance. The Wright R-3350 duplex cyclone engines powering the B-29 demonstrated American radial engine technology at its peak development. Each engine displaced 3,350 cubic inches, produced 2,200 horsepower at war emergency ratings, and incorporated features that Soviet engine designers had theorized about but never successfully implemented. The two-stage supercharger with intercooling maintained power output at high altitudes where single-stage designs lost effectiveness. The fuel injection system improved mixture distribution and allowed inverted flight without interrupting fuel flow, eliminating the carburetor icing problems that plagued Soviet engines. The magnesium alloy construction reduced weight while maintaining strength, using manufacturing techniques Soviet metallurgy had not mastered. Soviet engineers examining the R-3350 discovered that Wright Aeronautical Corporation had achieved specific power output, the horsepower per pound of engine weight, approximately 50% higher than the best Soviet radial engines. This advantage came from sophisticated metallurgy, precision manufacturing that allowed tighter tolerances and higher operating pressures, and advanced cooling designs that prevented detonation and pre-ignition at high power settings. Every component reflected manufacturing quality that Soviet factories struggled to achieve even when they understood the design principles involved. The crankshafts, machined from alloy steel forgings to tolerances measured in thousandths of an inch, the cylinder barrels, nitrided for wear resistance using surface treatment processes Soviet industry had not mastered, the valve springs, made from high-tensile steel that Soviet metallurgy could not reliably produce, all demonstrated the depth of American industrial capability. Disassembling the engines revealed construction techniques that Soviet engine builders found remarkable for their sophistication and attention to detail. The cylinder head assembly used sodium-cooled exhaust valves, a technology Soviet engineers knew about but had never successfully implemented in production engines. The hollow valves, partially filled with metallic sodium that melted at engine operating temperatures, transferred heat more effectively than solid valves, allowing higher power output without valve burning. Manufacturing these valves required precise welding to seal the sodium inside while maintaining exact valve dimensions and smooth surface finishes. Soviet attempts to replicate the process initially produced valves that leaked sodium, creating safety hazards and engine fires. The hydraulic systems operating landing gear, flaps, bomb bay doors, and numerous other aircraft functions used components manufactured to standards Soviet hydraulic specialists found remarkable. American SEALs maintained their effectiveness across temperature ranges from sub-zero high-altitude conditions to desert heat on the ground. Hydraulic pumps, driven by the engines through accessory gearboxes, maintained consistent pressure despite varying engine speeds and system demands. The entire hydraulic network, spanning the aircraft's length with multiple actuators operating simultaneously, demonstrated systems integration that Soviet designers admired but couldn't immediately replicate with available Soviet components. Soviet engineers discovered that American hydraulic system design reflected decades of commercial experience in construction equipment, agricultural machinery, and industrial applications where reliability directly impacted profitability. This broad industrial base gave American aviation access to proven components and design approaches developed through millions of hours of field operation in diverse applications. Soviet hydraulic technology, developed primarily for military applications without equivalent commercial foundation, lacked the depth and maturity that American systems demonstrated. The gap couldn't be closed quickly because it reflected fundamental differences in industrial development paths rather than specific technical secrets that could be stolen. By early 1945, as Soviet forces advanced into Germany and the Pacific War entered its final phase, the scope of the reverse engineering challenge had become fully apparent to Tupolev and his team. Simply copying the B-29 would require Soviet industry to develop entirely new manufacturing capabilities across multiple sectors. Aluminum alloys with properties matching American materials needed new metallurgical processes and quality control. Precision machining to tolerances Soviet factories rarely achieved in production required new machine tools and trained operators. Electronic and electrical components matching American specifications demanded manufacturing technologies Soviet electronics industry had not developed. The hydraulic seals, the pressure cabin gaskets, the countless rubber and synthetic components throughout the aircraft all required Soviet chemical industry to match American materials science. The challenge of replicating American materials proved particularly vexing because material properties depended on manufacturing processes as much as chemical composition. American aluminum alloys achieved their superior strength-to-weight ratios through precise control of heat treatment cycles that required furnaces capable of maintaining uniform temperatures within narrow tolerances across large batches of material. Soviet furnaces, designed for less demanding applications, produced temperature variations that resulted in inconsistent material properties even when chemical composition matched American specifications exactly. Engineers studying failed Soviet-produced components discovered that metallurgical structure varied significantly within individual pieces, creating weak spots that caused premature failure under stress. Stalin's directive to copy everything exactly created a fundamental dilemma for Soviet engineers and production planners. Exact copying meant reproducing American dimensions measured in inches and feet rather than metric units, creating conversion challenges throughout the production chain. It meant using American thread standards for fasteners rather than Soviet standards, requiring new tooling for every threaded component. It meant accepting American design approaches even when they conflicted with Soviet engineering practice or seemed inefficient by Soviet standards. The decision to proceed with exact replication rather than redesigning for Soviet manufacturing capabilities reflected Stalin's belief that American design represented proven effectiveness that Soviet modification might compromise. The fastener standardization issue created cascading problems throughout the supply chain that Soviet planners had not anticipated. The B-29 used American national fine thread standards for most structural fasteners, a system completely incompatible with Soviet metric threads. Soviet factories would need to manufacture thousands of different fastener sizes in the unfamiliar standard, requiring new threading dies, new quality gauges, and new inspection procedures. Workers accustomed to metric measurements would need training to distinguish between similar-appearing American sizes that differed by fractions of an inch. The accumulated cost and complexity of this single standardization issue exceeded the entire development budget for some Soviet aircraft programs. The reverse engineering process accelerated through early 1945 as teams completed documentation of major aircraft systems and began the painstaking work of creating production drawings that Soviet factories could use. Every component, from the smallest fastener to major structural assemblies, required detailed drawings showing dimensions, materials, manufacturing processes, and quality specifications. Soviet draftsmen, working from measurements and photographs of disassembled American components, produced thousands of technical drawings that would guide Soviet production efforts. The drawings had to be perfect because Soviet factories lacked the manufacturing flexibility to accommodate errors or ambiguities in documentation. The electrical system presented particular challenges for reverse engineering teams because American wire gauges, insulation materials, connector types, and circuit protection approaches all differed from Soviet practice. The B-29 used aluminum wiring in many circuits to save weight, a practice Soviet aircraft had never employed due to difficulties soldering aluminum and concerns about long-term reliability. American circuit breakers, resettable devices that Soviet aircraft didn't use, required Soviet electrical equipment manufacturers to develop entirely new products. The complex wiring harnesses, assembled with components from dozens of suppliers and routed through confined spaces in the fuselage and wings, demanded manufacturing processes that Soviet factories had never attempted at such scale and complexity. Examining the electrical system revealed American approaches to design documentation that differed significantly from Soviet practice. American electrical schematics used standardized symbols and conventions that made diagrams readable by workers across different contractors and facilities. Soviet electrical documentation, lacking equivalent standardization, often required interpretation by specialized engineers familiar with particular factory conventions. The American approach facilitated distributed manufacturing where multiple suppliers could produce components from identical documentation. Soviet practice, developed in a more centralized industrial system, worked adequately for simpler aircraft but proved inadequate for B-29 complexity. By mid-1945, with Germany defeated and Japan facing inevitable collapse, Soviet engineers had completed documentation of all three captured B-29s and begun the process of creating master patterns and tooling for Soviet production. The decision to proceed with full production despite the enormous industrial challenges reflected Stalin's determination to achieve strategic parity with America regardless of cost. The Soviet aviation industry received orders to prepare for B-29 production, designated Tu-4 in Soviet service as a Tupolev design despite being an exact copy of the American bomber. Factories across the Soviet Union began retooling to manufacture components for an aircraft far more complex than anything they had previously built. The production preparation revealed the true magnitude of the challenge Soviet industry faced. Boeing's Seattle plant, where most B-29s were built, employed over 30,000 workers with access to components from hundreds of suppliers across America's industrial base. Soviet planners attempting to recreate this production network found that many required components simply did not exist in the Soviet Union and would need to be developed from scratch. The specialized aluminum alloys, the high-strength steel forgings, the precision bearings, the hydraulic components, the electrical systems, and countless other items all required new Soviet production capabilities. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Soviet metallurgists struggled particularly with aluminum alloy production, discovering that American alloys used in the B-29 possessed properties Soviet aluminum could not match. American 24ST aluminum alloy, widely used in B-29 construction, achieved strength-to-weight ratios approximately 20% higher than Soviet equivalents through precise control of alloying elements and heat treatment processes. Soviet attempts to replicate the material initially failed because Soviet aluminum production lacked the purity control and processing precision required. Trace elements that American refineries removed through sophisticated processing remained in Soviet aluminum, degrading properties. Heat treatment processes that required precise temperature control and timing proved difficult to achieve consistently in Soviet furnaces designed for less demanding applications. The challenges extended beyond individual materials to complete manufacturing processes that American industry had perfected over decades of commercial aircraft production. Boeing's use of large-scale hydropress forming to create complex sheet metal shapes allowed rapid production of fuselage panels and wing skins with compound curves. Soviet factories lacked equivalent equipment and resorted to labor-intensive hammer forming techniques that required skilled craftsmen and produced less consistent results. American factories used massive drop hammers to forge crankshafts and other highly stressed components, achieving grain structures that resisted fatigue failure. Soviet forging capabilities lagged behind American practice in both scale and precision, requiring alternative approaches that often compromised component quality. The precision machining required for engine production particularly challenged Soviet capabilities. Wright R-3350 engines used cylinder barrels machined and honed to tolerances measured in 0.010 of an inch, achieving surface finishes that minimized oil consumption and maximized piston ring sealing. Soviet engine factories, even the best ones producing aircraft engines for fighters and ground attack aircraft, routinely worked to tolerances 10 times looser than American practice. Achieving B-29 engine specifications would require wholesale modernization of Soviet machine tool inventory, training of workers to higher precision standards, and implementation of statistical quality control processes that Soviet manufacturing had never systematically employed. Soviet factory managers, when presented with American specifications and told to match them exactly, initially believed the requirements represented American propaganda or deliberately inflated standards designed to impress allies. The reality that American factories routinely achieved such precision in mass production seemed impossible to managers accustomed to Soviet manufacturing, where each aircraft required individual fitting and adjustment to make components work together. The American concept that parts manufactured in different factories thousands of miles apart could be installed without custom fitting challenged fundamental assumptions about how complex machinery could be built. By late 1945, with the war ended and American B-29's having delivered the atomic bombs that forced Japanese surrender, Soviet engineers understood that copying the Superfortress would take far longer than Stalin's initial optimistic timeline had assumed. The target date for first flight of a Soviet-built B-29 copy kept slipping as industrial reality confronted political directives. Factories reported that they needed new equipment before they could manufacture components to specification. Suppliers indicated that materials development would require years, not months. Quality control specialists warned that achieving American manufacturing consistency would demand fundamental changes to Soviet production culture and worker training. Tupolev, reporting directly to Stalin on project progress, had to balance honest assessment of challenges against the leader's impatience with obstacles and excuses. The aircraft designer had survived Stalin's purges once and had no intention of providing reasons for another arrest. Progress reports emphasized achievements while downplaying setbacks, creating optimistic timelines that engineers on the factory floor knew were unrealistic but dared not contradict publicly. The gap between political demands and industrial reality grew as the project continued, creating tensions that would characterize Soviet weapons development throughout the Cold War era. Engineers working on specialized systems found themselves caught between technical impossibility and political necessity. The computing gun sight, for instance, required precision gears and bearings that Soviet machine tools couldn't produce to American tolerances. Engineers proposed simplifications that would make the device producible with Soviet capabilities, but Tupolev rejected any deviation from exact copying based on Stalin's directive. The result was a gun sight that looked identical to the American original but functioned less reliably because Soviet manufacturing couldn't achieve the precision that made American fire control work properly. Similar compromises occurred throughout the aircraft as Soviet industry struggled to match American manufacturing quality. The first Soviet-built Tu-4, assembled from components manufactured in factories across the USSR, finally rolled out for ground testing in late 1946. More than 2 years after the first B-29 landed in Soviet territory. The aircraft looked identical to the American original from external appearance, but Soviet engineers knew that beneath the copied skin lay thousands of compromises where Soviet manufacturing capabilities couldn't quite match American specifications. Some components used Soviet materials that approximated but didn't perfectly replicate American properties. Other systems employed Soviet manufacturing methods that achieved similar results through different processes. The accumulated effect of these small deviations from perfect replication created uncertainty about whether the Soviet copy would perform like the American original. Ground testing revealed numerous problems that required troubleshooting and modification before flight testing could proceed. Hydraulic systems leaked at seals where Soviet gasket materials didn't maintain integrity under pressure and temperature cycling. Electrical systems showed intermittent failures where Soviet wire insulation degraded from vibration and temperature exposure. Engine installations required modifications because Soviet engine mounts didn't quite match American designs, creating vibration problems that threatened structural damage. Each problem, when investigated, traced back to Soviet manufacturing limitations that made exact replication of American quality impossible despite understanding American design intent. The first flight of a Soviet-built Tu-4 occurred on May 19, 1947, nearly 3 years after the first B-29 reached Soviet territory. Test pilot Nikolai Rybko took the controls for a flight lasting 1 hour and 10 minutes that demonstrated basic airworthiness but revealed performance shortfalls compared to the American original. Maximum speed fell approximately 10% below B-29 specifications due to engine power output that Soviet production couldn't quite match despite copying the R-3350 design exactly. Service ceiling similarly fell short because Soviet engines lost power at high altitude more rapidly than American originals. Range proved adequate but still less than American B-29's achieved because Soviet fuel consumption ran higher due to less efficient Soviet manufacturing of engine components. Soviet flight testing continued through 1947 and into 1948, gradually expanding the Tu-4's performance envelope and identifying problems that required correction before series production could proceed. The pressurization system worked but leaked more than American specifications allowed, requiring cabin compressors to work harder and reducing crew comfort at maximum altitude. The defensive armament functioned properly, but the computing gun sights sometimes produced erratic solutions because Soviet gyroscope manufacturing couldn't match American precision. The radio and navigation equipment operated acceptably, but with less reliability than American originals because Soviet electronics manufacturing used vacuum tubes that failed more frequently than American equivalents. Every test flight, every system evaluation, and every maintenance inspection reinforced the same fundamental lesson that Soviet engineers had learned through 3 years of intensive reverse engineering effort. Copying American design exactly was possible with sufficient effort and resources. Matching American manufacturing quality was far more difficult and in some cases impossible with Soviet industrial capabilities circa 1947. The Americans hadn't built a better bomber simply through superior engineering knowledge that could be stolen and replicated. They had built it through industrial maturity developed over decades of commercial manufacturing that emphasized consistent quality, process control, and manufacturing precision that Soviet industry had never needed to achieve for its primarily military production. The recognition that manufacturing quality mattered as much as design knowledge represented a psychological shift for Soviet engineers trained in a system that celebrated theoretical brilliance and revolutionary innovation, but often neglected the unglamorous work of perfecting production processes. Soviet education produced excellent theoretical scientists and creative designers who could conceive advanced technologies and solve complex engineering problems. But Soviet industry lacked the depth of manufacturing expertise that American companies had developed through intense commercial competition in consumer markets where quality and reliability directly impacted sales and profitability. Soviet factories, protected from market forces and evaluated primarily on quantity produced rather than quality achieved, had never developed the manufacturing culture that made American industrial dominance possible. Stalin ordered series production of the Tu-4 to proceed despite performance shortfalls because even an imperfect copy of the B-29 gave the Soviet Union strategic bombing capability far superior to anything Soviet design bureaus could have produced independently in the same timeframe. The first production Tu-4s entered service with the Soviet Air Force in 1949. Providing a credible nuclear delivery capability that influenced American defense planning throughout the early Cold War. Western intelligence, uncertain whether Soviet atomic weapons development had progressed as rapidly as feared, now faced the certainty that the USSR possessed bombers capable of reaching American allies in Europe and potentially American territory from forward bases. But Soviet military planners understood that possessing Tu-4s and possessing the industrial depth to sustain a strategic bombing campaign represented fundamentally different capabilities. The Americans had built over 3,700 B-29's during the war and could have continued production indefinitely at rates Soviet industry couldn't approach. Soviet Tu-4 production proceeded slowly, hampered by component shortages, quality problems, and manufacturing bottlenecks throughout the supply chain. By the time production ended in 1952, Soviet factories had completed approximately 1,200 Tu-4s, less than one-third of American B-29 production despite having the complete design blueprints and several years of manufacturing experience. The production numbers told only part of the story. Soviet Tu-4 operational readiness rates ran significantly below American B-29 statistics because Soviet aircraft required more frequent maintenance and suffered higher component failure rates. Soviet engines needed rebuilding after fewer flight hours than American engines because Soviet manufacturing couldn't match the precision and material quality that gave American engines their durability. Soviet hydraulic systems leaked more frequently because Soviet seals degraded faster than American equivalents. Soviet electrical systems failed more often because Soviet components lacked the quality control that made American electronics reliable. The accumulated effect of these quality shortfalls meant Soviet Tu-4 units maintained fewer operational aircraft per unit assigned strength than comparable American B-29 units. The maintenance burden created additional problems for Soviet logistics systems that struggled to support complex aircraft operating far from industrial centers. The B-29 had been designed with field maintainability in mind, incorporating features that simplified servicing under austere conditions without specialized facilities. But Soviet copies, assembled with components that didn't quite match American quality, often required more intensive maintenance than the American original. Soviet maintenance personnel, trained on simpler aircraft, needed additional training to properly service the sophisticated systems the Tu-4 copied from American design. The training challenge was compounded by Soviet secrecy surrounding the aircraft's American origins, with technical manuals avoiding any mention that the Tu-4 was a reverse-engineered copy rather than an original Soviet design. Western intelligence gradually pieced together the Tu-4's origins through various sources, including debriefings of Soviet personnel who defected or were captured, technical intelligence collection that identified American components in crashed or captured Tu-4s, and photographic reconnaissance showing the unmistakable similarity between Soviet bombers and American B-29's. The revelation that Soviet strategic bombing capability rested entirely on copied American technology rather than indigenous Soviet development influenced Western assessments of Soviet industrial capability and technological sophistication. If the Soviets needed to copy American bombers rather than designing their own, what did that imply about Soviet ability to develop other advanced weapons systems independently? The psychological impact within the Soviet Union of knowing their premier strategic bomber was an American copy rather than a Soviet design created tensions that affected aviation development for years. Soviet engineers, proud of accomplishments in fighters, tanks, and other areas where indigenous Soviet designs competed successfully with Western equivalents, resented the implicit admission of inferiority that reverse engineering represented. Tupolev himself, despite successfully leading the copying effort and receiving recognition and awards for the achievement, understood that future Soviet bombers needed to be original Soviet designs rather than copies if Soviet aviation was to claim technological parity with the West. The effort did, however, provide Soviet industry with detailed exposure to American manufacturing methods and quality standards that influenced subsequent Soviet aviation development. Engineers who had struggled to replicate American precision machining, sophisticated metallurgy, and advanced manufacturing processes understood what Soviet industry needed to achieve to compete with American capabilities. Some of these lessons transferred to other Soviet programs, gradually improving manufacturing quality across Soviet aviation. But the improvement came slowly because systemic changes to manufacturing culture, worker training, and quality control required sustained effort and resources that Soviet planners often diverted to other priorities. By the early 1950s, as the Tu-4 force reached peak strength, Soviet designers had already begun developing replacement bombers using original Soviet designs rather than copied American technology. The Tupolev Tu-16 Badger and later the Tu-95 Bear represented indigenous Soviet strategic bombers that incorporated lessons learned from studying the B-29 but reflected Soviet design philosophy rather than American approaches. These aircraft demonstrated that Soviet aviation could produce capable long-range bombers when allowed sufficient development time and resources. But the fact that Soviet design bureaus needed nearly a decade to develop indigenous designs with capabilities comparable to what the B-29 had demonstrated in 1944 highlighted the technological gap the reverse engineering program had temporarily closed through copying rather than innovation. The three B-29s that emergency landed in the Soviet Union during 1944 had accomplished what no Soviet espionage operation or design effort could have achieved in the available time. They provided Stalin with strategic bombing capability that influenced early Cold War nuclear deterrence calculations and potentially altered the course of history. Without the Tu-4, Soviet nuclear weapons development, successful as it proved, would have lacked delivery systems capable of striking American allies or threatening American territory. This capability gap might have emboldened American policymakers to take more aggressive actions during the Berlin blockade, the Korean War, or other early Cold War crises. But the three B-29s also revealed to Soviet engineers the magnitude of American industrial superiority in ways that statistics and intelligence reports never could. Holding American components in their hands, measuring American precision machining with their instruments, and struggling to replicate American manufacturing quality in their factories taught Soviet engineers that industrial maturity couldn't be stolen or copied like a design blueprint. The knowledge that American industry routinely produced quality that Soviet industry struggled to achieve even when given exact specifications and years of effort proved more sobering than any intelligence estimate of American production capacity. The Americans, for their part, continued developing bomber technology through the late 1940s and into the 1950s, producing aircraft that rendered the B-29 obsolete even as Soviet factories struggled to produce adequate copies. The Boeing B-47 Stratojet, entering service in 1951, represented a quantum leap in jet bomber technology that Soviet aviation couldn't immediately match. The Boeing B-29 Superfortress, beginning development in the late 1940s, would provide American Strategic Air Command with capabilities far exceeding anything the Tu-4 could offer. By the time Soviet industry had mastered B-29 production, American industry had moved on to next-generation technologies that maintained American advantages despite Soviet copying efforts. Soviet test pilots who flew both captured B-29's and Soviet-built Tu-4s could feel the difference in manufacturing quality even though external specifications matched closely. American bombers exhibited refinement in control responses, smoothness in system operation, and reliability in component function that Soviet copies couldn't quite replicate. The differences were subtle, individual characteristics that didn't appear in specification sheets, but they revealed themselves to experienced pilots who understood what excellent aircraft felt like. American aircraft felt finished, polished, refined through attention to details that Soviet manufacturing rushed past in the drive to meet production quotas. Maintenance personnel similarly noticed quality differences when servicing Soviet copies versus the few captured American originals that remained in Soviet service for test and evaluation. American components wore more evenly, failed less frequently, and generally behaved more predictably than Soviet copies made from nominally identical materials to apparently identical specifications. The differences traced to manufacturing quality variations too small to appear in drawings or specifications but significant enough to affect long-term reliability and performance. American factories achieved consistency that Soviet factories struggled to match because American manufacturing employed statistical process control, systematic quality assurance, and worker training that emphasized precision over speed. By 1953, when Stalin died and Soviet aviation began transitioning to new indigenous bomber designs, the Tu-4 had served its purpose of providing interim strategic capability while Soviet industry developed manufacturing expertise and Soviet designers created original bombers. The aircraft remained in service through the 1950s, gradually replaced by more capable indigenous designs as they became available. Some Tu-4s were converted to specialized roles including aerial refueling, electronic warfare, and transport missions that utilized their long range and large payload capacity. A few survived into the 1960s before final retirement, having given the Soviet Union nearly 15 years of service from a design stolen wholesale from American industry. The legacy of the Tu-4 program extended far beyond the aircraft itself to influence Soviet approaches to technology acquisition and weapons development throughout the Cold War. The success of reverse engineering the B-29, measured by Soviet ability to field strategic bombers based on American design, encouraged Soviet leadership to emphasize intelligence collection and industrial espionage as legitimate paths to military capability. Soviet intelligence services devoted enormous resources throughout the Cold War to stealing Western technology, acquiring documents, recruiting scientists, and obtaining components that could be copied or reverse engineered. Some of these efforts succeeded spectacularly, giving Soviet industry access to advanced technologies years before indigenous development could have produced equivalent capabilities. But the B-29 experience also taught Soviet engineers that stolen design information alone couldn't overcome industrial limitations rooted in decades of different manufacturing priorities and development paths. Copying could accelerate capability development and close technological gaps temporarily, but sustaining competition with American industry required building genuine Soviet manufacturing expertise rather than relying perpetually on copied American technology. This lesson influenced Soviet aviation development through subsequent decades as design bureaus moved away from direct copying toward developing indigenous designs that incorporated lessons learned from studying Western technology without slavishly reproducing Western approaches. The three American bombers that emergency landed in Soviet territory during 1944 had been unremarkable members of a fleet of thousands built by American industry. Their crews certainly never anticipated that their aircraft would become templates for Soviet strategic bombing capability or that their emergency landings would trigger one of history's most ambitious reverse engineering programs. The bombers themselves, after being exhaustively documented and tested, eventually disappeared into Soviet storage facilities or were scrapped for materials as Soviet factories produced copies that made the originals unnecessary for reference. But the impact of those three aircraft echoed through decades of Cold War competition and fundamentally altered Soviet understanding of American industrial capability. Soviet engineers who had believed that American technological advantages could be overcome through superior Soviet theoretical knowledge and revolutionary innovation discovered that industrial maturity developed over decades through commercial competition represented advantages that couldn't be quickly or easily replicated. American factories didn't just build aircraft, they built them with consistent quality, reliable components, and manufacturing precision that Soviet industry needed years to approach even when given complete design information and unlimited resources. The psychological impact of this recognition affected Soviet engineering culture in ways that persisted long after the Tu-4 retired from service. Soviet engineers learned to respect American manufacturing capability even when they believed Soviet design creativity equaled or exceeded American approaches. They understood that building prototypes and building production aircraft represented fundamentally different challenges, with American industry demonstrating consistent superiority in transitioning advanced technology from laboratory to production line. This knowledge tempered some of the revolutionary enthusiasm that characterized early Soviet aviation, replacing it with more realistic appreciation for the sustained effort required to develop genuine industrial capability rather than simply copying successful foreign designs. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe. The story of Soviet engineers reverse engineering 3 captured B-29's revealed that technology transfer through copying faced fundamental limits that no amount of effort could completely overcome. The Soviets copied American design exactly, creating aircraft that looked identical and performed similarly, but they couldn't copy the industrial culture, manufacturing experience, and quality consciousness that made American production consistently superior. Those intangible advantages, developed through decades of commercial manufacturing in competitive markets, represented America's true technological edge, the edge that persisted throughout the Cold War despite Soviet efforts to close the gap through espionage, copying, and massive resource allocation to military industry. The 3 B-29's taught Soviet engineers everything they needed to know about American bomber design and revealed truths about American industrial superiority that Soviet planners had been reluctant to acknowledge. Understanding your opponent's advantages doesn't eliminate them or create equivalent capabilities when the advantages rest on industrial depth developed over generations. The Soviets learned this lesson through 3 years of intensive reverse engineering effort that produced capable bombers but also revealed the magnitude of challenges that copying alone could never overcome. The recognition that industrial maturity mattered as much as design knowledge would influence Soviet weapons development throughout the Cold War, shaping strategies and priorities as Soviet industry struggled to achieve genuine parity with American manufacturing capability rather than merely copying American designs.